Well, hey! Previously in class, we had looked a little bit at parametric equations. So I'd like you to right now just pause this and go ahead and try to find each of these things. The first derivative, the second derivative of y with respect to x, and the length of the curve from t equals pi to t equals the square root of 15. And you just have to set up that last one. So let's see if we can do that, and then unpause this video and we'll take a look at it. Okay, so if we want to find the derivative of y with respect to x, well, we're going to take a look at our x component and our y component, because remember, parametric equations, they're controlled separately. Our x's and our y's of our ordered pairs are controlled by the value of t. And so if we take the derivative of x with respect to t, we're with respect to t, so that's nice. It's going to be 2t plus 6. And we take the derivative of y with respect to t. That's going to be pretty simple. It's going to be negative 12t cubed. And we set it up. It is dy over dx. That's going to be dy over dt divided by dx over dt. And so we have negative 12t cubed over 2t plus 6. Does it simplify a little bit? We can divide everything by 2, and we get a negative 6t cubed over t plus 3. And that is our first derivative, our derivative of y with respect to x. Negative 6 t cubed over t plus 3. Now the second derivative, and remember we're applying, we just found dy over dx, and we are applying another derivative to that. We're taking the derivative with respect to x of dy over dx. That's what's getting us this notation right here. So we're going to take our first derivative, and we are going to take the derivative of that with respect to x. So we've got a big quotient rule. So I'm going to go low d high. Low d high is going to be t plus 3 times the derivative of the upper function right there, the high, negative 18t squared. But because I'm taking the derivative with respect to x, I do have to apply the chain rule. I can see I'm going to run out of space right here, so I'm going to restart this. Low d high because I was taking the derivative of t with respect to x, implicit differentiation, our chain rule, minus high d low, the derivative of t plus 3 would be 1 times dt over dx. Low squared, t plus 3 squared. Obviously this isn't going to, if it doesn't simplify down that much, it's okay, it's not the end of the world. But we now have our dt over dx. dt over dx, if this was dx over dt, dt over dx would be the reciprocal. It'd be 1 over 3 times t, sorry, 1 over 2 times t plus 3. I just write it like that because I know we did a bunch of simplifying later. It's probably going to be helpful to go ahead and pull out that 2. And now when I plug in the dt over dx, right here, notice that the t over 3 on top, the t over 3 on the bottom will cancel out. We have a 1/2. 1/2 times negative 18 gives me a negative 9t squared. minus, really plus, because we're subtracting a negative 6t cubed. Well, the positive 6 rather, divided by 2 gives me a 3t cubed over t plus 3. All of this is still being divided by t plus 3 squared. We could then divide everything by t plus 3 squared. It would simplify down a little bit more, but this isn't super necessary to make this negative 9t squared over t plus 3 squared plus 3t cubed over t plus 3 cubed. And that's not a super necessary final step. But what is super necessary, regardless of how far we decide to simplify it, is plugging in that dt over dx. And so I did some stuff in my head because writing all this out, I would run out of space real quick. So hopefully all that, we're remembering those steps. Finally, the length of the curve. Well, when we're talking about parametric equations and the length of the curve, our formula is from our t equals a to t equals b, our lower t to our upper t, we're accumulating the square root of dx over dt squared plus dy over dt squared with respect to t. So we just want to set this up with our dx over dt and our dy over dt. We're just setting it up. We aren't solving it. We're not simplifying it. We don't do any of that. So we're going to go from pi to the square root of 15, our lower to our upper t's. Square root of dx over dt is 2t plus 6 squared plus dy over dt is a negative 12t cubed squared, and we are going to be with respect to t. All right, so just some quick finding the parametric equation stuff. Hopefully that stuff isn't that crazy. It's pretty straightforward what we would want it to be. All right, let's talk about something that feels very similar to parametric equations, but is very much different. We need to think about it in a different way, even though you want to treat it the same way. So we're going to create a scenario and hopefully it all makes sense. So first of all, we have our notation for a vector. You might remember this notation if you've seen vectors before in physics or some science course, but this is our notation for a vector, and in here we will have an x component and a y component to our vector. And when I write that, you're probably thinking, wow, that's really similar to our parametric equations. All right, and I wish it didn't seem so similar because then we wouldn't get them confused. Now, a vector in itself is a direction. This right here, this vector, as we see it, this is an x component and a y component. A vector is a direction. So let's see how this all works out. How I have best grasped this idea is to imagine a room. All right, we've got a room and we're looking down on this room. We've got, I don't know, we're up above it. We're looking down on this room, and let's imagine the door is over here in the corner, and from that door we have an x direction and we have a y direction. Okay, kind of like a coordinate plane, right? Yeah. And let's imagine that we have released a rat. Okay, here's our little rat friend. And this rat can just run wherever, okay? The rat can run in the x direction, the rat can run in the y direction, the rat can run around the room. And the rat is being modeled by this vector valued function. And yeah, if we plug in a value for t, it's giving us a location of this rat, essentially. Right? If we plug in some value for t and we find that the rat is over here, well, this vector is telling us the location, but we really don't need to think of it as a location as much as it has told us a direction from the origin, from the point of release, from the point of origin for the starting, the initial place. This is the direction from that initial place that our rat is currently in. There is some x distance over. We have gone some x distance over. We've gone some y distance up. And if we wanted to know the distance the rat currently is from the origin, we would call that the magnitude. The magnitude would be the distance from the origin, pop, pop, for magnitude. And to find the magnitude, we'd use Pythagorean theorem. Look at that. Notice the magnitude is the hypotenuse. We could use Pythagorean theorem. The magnitude, the distance from the origin the rat currently is at this point, would be the hypotenuse. So we could find the magnitude would be the square root of the x component squared plus the y component squared. The magnitude is going to be pretty important for us in a second. Now, here's what we need to realize. This is the most important thing, okay? dy over dx, right? We found dy over dx for parametric equations. We even found the second derivative, but what in the world does dy over dx represent here? dy is just remember, we're looking down upon this rat. dy is just the change in this direction, and dx is just the change in this direction. dy over dx is not the velocity. dy over dx doesn't really give us anything. It doesn't tell us, it tells us the rate of change of our rat on this grid, but who cares? I don't think I'm going to be asking you that question anytime soon. But what is more interesting is how fast is that rat actually moving? Isn't that more interesting? What direction is that rat moving from where it's currently at, and so on? Because this is just telling us the direction from the origin, but in what direction is our rat actually moving from where it currently is? All of that is more interesting. So let's talk about how to find the velocity and even acceleration of a vector valued function. Let's look at this one right here. So we're given a position vector. Here it is, a position vector. We've got an x component, a y component, boom, boom, boom. We can see our notation, all that's good. And first, we want to find the particle's velocity vector at t equals 2. So look, this is going to be way easier than what you could possibly expect. All right, you ready? You excited? Our velocity vector, here we go. Our velocity vector. Well, we take the derivative of the x component. We take the derivative of the y component. We found our velocity vector. Oh, sorry, we do want it at t equals 2. So our velocity vector, and I really should use a little notation like that, saying this is the velocity vector, it's a little vector symbol. Our vector velocity at 2 would be 2 cubed is 8 times 4 is 32 minus 3 is 29. And 14 times 2 is 28. That is our velocity vector at 2. Oh, you know what's coming. The acceleration vector, all right, let's do our acceleration vector. Well, we're going to take the second derivative, right? You like these now. You like them more than you thought you would. Our acceleration vector at 2, of course, would be 2 squared is 4 times 12, 48. And 14 doesn't change. Done. We got it. Now, these are vectors. Remember, a vector is a direction. A vector's telling us a direction. And if we want to find the actual velocity, the actual speed, the actual acceleration, well, just added some. Find the magnitude of the velocity. Well, the magnitude, pop, of the velocity, magnitude is when we need to use Pythagorean theorem. Magnitude will be the actual velocity. What is the actual speed? The speed is found on the magnitude. The vector was the direction. The magnitude is the actual speed. Because remember, velocity is speed with a direction. So here, let's find the actual speed. The magnitude will be, here we go. Just going to do it over here. The square root of 29 squared plus 28 squared. We could type that in the calculator. I think we can handle that. Same thing, the magnitude of the particle's acceleration. Well, it would be 48 squared plus 14 squared. Yeah, it's what you want. It's what you want. All right. So, with that, try this one out right here. You got a position vector. You want to find the particle's velocity vector, the magnitude of the velocity. Remember, the vector is the direction. The magnitude is the actual speed. Acceleration has a direction as well. What direction are we accelerating will be our vector and the magnitude of the acceleration. All right, pause this, try that out. Good, now let's try it ourselves. Well, sorry, you just tried it, now it's time for me to try it. The velocity vector would be a negative 3t squared plus 2, comma 8t. The velocity vector at 3 no one's here to tell me if I did anything wrong, so I hope I'm getting all this for you. The velocity vector, the magnitude would be the square root of negative 25 squared plus 24 squared. I'm sure you could handle that. That would tell us our actual. And if we were given some units, like whatever it would be, feet per second, units per minute, whatever. We could have units for that because velocity is a rate of change. Acceleration vector, we know we would take that second derivative. We're good at those. Our acceleration vector at 3. Again, hopefully I'm getting all these right so you're not laughing at me right now. And the magnitude, of course, would be the hypotenuse. Setting up Pythagorean theorem, typing that in. You could do it, you could do it. All right. Better than we thought, right? Way better than we thought. I know it is. I know it's a lot less bad than you probably thought it would be. Cool. Questions? I can't answer them right now anyway. All right, let's look at a a weird little question here. It says a particle moves along the curve xy equals 12 so that the y coordinate is increasing at a constant rate of 2 units per minute. What's the rate of change in units per minute of the particle's x coordinate when the particle is at the point 3, 4? Woo, woo. Dun, 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 dun. Well, I hear rate of change of the x coordinate. So we are looking units per minute. We're talking about per time. We're looking for this, dx over dt, at the point 3, 4. So if I'm looking for dx over dt and I've got this function, and they also told me my y-coordinate, my rate of change of my y-coordinate, is 2 units per minute. And they've given me all kinds of stuff. So I'm going to take this xy. I'm going to take the derivative with respect to t. This is pretty much a related rate situation, except for we're now thinking about velocity and all kinds of stuff. Well, derivative of the first times the second, product rule, plus the derivative of the second times the first. Derivative of 12 is 0. If I plug in everything I do have, I've got a y, I've got an x, y, x, and I even have the rate of change of y. So I've got dx over dt times 4 plus 3 times dy over dt, which is 2. Add over the 6, sorry, subtract over the 6. Divide by 4, and we've got a dx over dt, what we were looking for, of negative 3 over 2 units per minute. Now we want to know the magnitude of the velocity when the particle's at the point 3, 4. So we've accumulated here the change in our x, the change in our y. Right? If we wanted to set this up as a velocity vector, it would be negative 3 over 2, 2. The magnitude of the velocity, well, at this point, we're going to take our x-coordinate, we're going to square it, we're going to add it to our y-coordinate squared. And that's going to give us our actual speed. Here we have the direction of our velocity. Here we have the actual speed component of our velocity. I'm sure we could square it, we can do all that. The magnitude of our velocity would be in units per minute. Okay, cool. Take a look at this one right here. Very, very similar, very similar. Wow. Wow, so similar. All right, so let's try this one out. So I've got a function. I'm looking for the rate of change first of the y-coordinate. I was given that the x-coordinate is increasing at 3 units per minute. And looking at the point 24, so I'm going to take dy over dt equals 6x dx over dt minus 4 dx over dt. Dy over dt is already solved for me. Wow, this is nice. I can just plug in my x-coordinate of 2. Dx over dt is 3. And dy over dt comes out to be 36 minus 12, 24. and we are in units per minute. Now our velocity vector at this moment with our x component, our y component, 324. The magnitude, pop, pop, of our velocity would be the x component of our velocity squared plus the y component of our velocity squared, and we would still be in units per minute.